Our next programme is for the second level Introduction to Pure Mathematics course. It looks at the formal ideas of integration and area.
In this programme, we're going to link integration with area. Now, you'll remember that in the introduction to the course, we talked about defining the area of a region such as this in the plane, and we used a method based on square counting. Well, now that we've got a bit of machinery from analysis at our disposal, we can make some of these ideas more precise. And to start with, we'll make the idea of square counting precise by using what's known as a rectilinear region. Inside the region here, we've drawn another region with horizontal and vertical line segments for its boundary. And we call such a region a rectilinear region. And the area of such a region, which is very easy to define, is called an inner estimate for the area of R. And what we want to do is to consider all these rectilinear regions. Well, there's obviously going to be quite a few of them. For instance, we could have a small one like that. And each one of these gives us an inner estimate. And what we want to do is to consider the set of all these inner estimates. The set of inner estimates is bounded above. That's saying no more than that the region can be fitted inside some rectangle of area Q, say. Q is an upper bound for the set of all the rectilinear areas that we can fit inside R. That is, the set of all inner estimates. We can find the areas of all the rectilinear regions. We'll call the set of these inner estimates L. Now, L is bounded above by Q, so it has a least upper bound. And this is what we'll call the inner area of the region. So we've defined the inner area of the region R, and it's the least upper bound of this set L, the set of inner estimates. And intuitively, you can think of taking bigger and bigger inner estimates, getting as close as possible to the region R, and that's the inner area. And there's a similar notion of the outer area. To define the outer area, you consider rectilinear regions that fully enclose the region R. The area of each one of those gives an outer estimate for the region. And you take the set of all the outer estimates, and you take the greatest lower bound of U. And then intuitively, you can think of that as obtained from outer estimates, which creep closer and closer to the region R. So we've got a notion of an inner area and an outer area. And for a nice smooth boundary curve like this, it's pretty clear that the inner and the outer area are going to coincide. But it's not so clear if you consider a region which has a very fuzzy boundary. Then perhaps the inner and the outer area might not be the same. Well, in any case, whatever happens, whenever we have a bounded region, we have a notion of inner area and of outer area, and if they coincide, then we'll say that our region has an area, and this coincident value we'll take to be the area of the region. So, with this notion of inner and outer area, we've made our idea of square counting very precise.
Well, now let's consider functions. If we have a bounded function, like this one, then, associated with the interval AB, we have a natural region R. The region bounded by the graph of the function, the ordinates x equals a and x equals b, and the x-axis. Well, now in this example, the function that we've taken is everywhere positive on AB. And it's quite clear that the area associated with that region ought to turn out to be a positive real number. But now what about a function like this one? This function has its graph dipping below the axis. And the region associated with the interval AB consists of a part above the axis and a part below. Well, now I have a slight problem as to how to interpret this region corresponding to the part below the axis, where the function f takes negative values. Well, it turns out that what we have to do when investigating the area associated with functions like this is for each of the parts of the region below the axis, their contribution to the area has to be counted negatively. Well, the full details of that are spelled out for you in the correspondence text. And for the purposes of this program, we're going to restrict ourselves to this idea. We're going to look at functions which are positive on AB. Well, now this region R and regions like it, which are beneath a well-behaved function, are obvious candidates for the sort of region that ought to have an area in the sense that Colin has just described. So with this sort of area in mind, we'll introduce some new notation which is going to help us in our search for area. Since f is a bounded function, we know that our region has an inner area, and we call its value the lower integral of f on AB. We write it with an ordinary integration sign and put a bar underneath. Similarly, we have an outer area, and we call its value the upper integral of f on AB. This time the bar is above. If the lower and upper integrals coincide, that is, if the region has an area, then we call the value of that area the Riemann integral of f on AB. We write that with an ordinary integration sign.
So the Riemann integral is the area of this region under the graph of f, provided that area exists. Well, we haven't as yet proved anything about the existence of areas, and that's exactly the point. That's exactly what we're going to prove in this program. We're going to prove that provided our function f is continuous, then this area exists. In other words, the Riemann integral exists. And then we're going to establish a very strong connection between integration and primitives. We're going to prove the fundamental theorem of the calculus. And what that says is if you take this function capital F of x, which is the integral up to x of f, in other words, the area so far function, and if you differentiate it, you get back to f again. In other words, capital F of x is a primitive of little f. And that will have tied up this approach to integration with the approach in the rest of the unit, where you'll remember we assumed that primitives exist. Well, that's what we're going to prove, but we're not going to prove these things directly. What we're going to do is we're going to take a little logical sidestep, and we're going to axiomatize the idea of integration. We're going to introduce an axiomatic integral function which satisfies two axioms, and then we're going to prove two theorems. The two theorems together will imply all the results we want, including the fundamental theorem of the calculus. So, what we've got to do first is to look at those two axioms for an integral function.
An integral function for f on AB is a function defined on all subintervals of AB. It assigns to the subinterval alpha beta a real number which we denote like this, I from alpha to beta of f. And this real number is meant to capture the idea of the area of this strip. So when we come to choose our axioms now, it's helpful to keep this picture of the area in mind. But remember that we're going to define the integral function abstractly from two axioms. We're not going to define it specifically as this area. The two axioms that we choose are called the additivity axiom and the boundedness axiom. The additivity axiom simply says that if alpha beta and beta gamma are two subintervals of AB, then the value of the integral function on alpha beta added to the value of the integral function on beta gamma is equal to the value of the integral function on the bigger subinterval alpha gamma. The boundedness axiom says that the value of the integral function on alpha beta fits between the areas of two rectangles of heights little m and capital M, one above the graph and the other below, where little m and capital M are the bounds of f on the subinterval alpha beta. So there's our definition of an integral function. We've defined it with the idea of area very much in mind. The two axioms that we've laid down correspond to obvious properties that we'd expect area to have. But notice that it was an abstract definition. An integral function for f on AB is any function at all defined on the subintervals of AB satisfying the two axioms, the additivity axiom and the boundedness axiom. Well, now we're ready for our first theorem. It's this. We're going to look at continuous functions little f. If we've got any continuous function little f and any integral function I for f on AB, then associated with the integral function we have this function. Capital F of x is equal to I from a to x of little f, where notice that a is a constant That's the left-hand endpoint of the interval AB, and consequently, capital F is a function of the single variable x. We call it the integral so far function. Now, what our theorem says is that for any integral function I, the integral so far function capital F is a primitive of little f. That is, little f is the derived function of the integral so far function. Well, now let's prove that theorem. Remember that capital F of c is I from a to c of f. And in general, capital F of x is I from a to x of f. Now we're trying to prove that little f is the derived function of capital F. And to get at the derived function, we investigate the chord-slope function, capital F of x minus capital F of c over x minus c. Well, capital F of x minus capital F of c is I from c to x of f. That's by the additivity axiom. And by the boundedness axiom, that is equal to the area of a rectangle somewhere between these bounds. When we divide by x minus c to get the chord-slope function, we get a height, or a value of f, somewhere between the bounds. Now we're interested in the differentiability of the function capital F, and for that we investigate the chord-slope function, and we're interested in this general point C. But notice that as yet we've not defined the value of the chord-slope function at C itself. Well, if we recall that what we're trying to prove is that d of f equals little f, it tells us that the value that we want for the chord-slope function at C is little f of C. So we make that definition. And our task now is this. We want to show that when we've given the chord-slope function value f of c at C, we want to show that it's continuous at C. Well, it's not a difficult task from here. We've already done most of the work. If we combine what we've already done with the fact that little f is continuous, we're just about home. The precise details are spelled out for you in the correspondence text, but let's here illustrate how the argument goes. First of all, let's just recall what we mean when we say the function little f is continuous at C. That means that if we take any nest of intervals converging to C, the images under f give rise to a nest of intervals converging to f of C. Well, now our interest is in the continuity of the chord-slope function. So how can we tie that into the continuity of little f? Well, look at the argument we've already established here. On this interval, from C to x, we've seen that the values of the chord-slope function are trapped between little m and capital M. And little m and capital M are the bounds for the function little f on this interval. In other words, the values of the chord-slope function are contained in the least closed interval containing f of the interval Cx. Well, the same would be true for any interval we take down here containing C. So if we take a nest converging to C, the images under the chord-slope function are going to be contained in a nest which, by the continuity of the function little f, converge to f of C. And that's exactly what we want. Now, the important thing to notice in this argument is that although I've appealed a lot to the picture here, we've really only used the two axioms for an integral function. Let's just quickly look through the main steps of the argument again and see where the axioms came in. We're interested in the differentiability of capital F at the general point C, and for that we investigate the chord-slope function. The first thing we did was to use the additivity axiom. The additivity axiom simplified the numerator for us. It tells us that capital F of x minus capital F of c is just I from c to x of f. Well, then we use the boundedness axiom here. Because here we've got now I from c to x of f, and the boundedness axiom tells us that that's contained between these bounds, little mx minus c and capital M of x minus c, where little m and capital M are the bounds of the function little f on the interval Cx. Well, now that gives us this step, which tells us that the values of the chord-slope function lie between little m and capital M. Well then finally, the continuity of the function little f gave us the continuity of the chord slope function as we required.
So that's proved theorem 1. It's proved that if we have an arbitrary integral function, then it gives rise to a primitive. And notice that it's just like the statement of the fundamental theorem, except that it's got this arbitrary integral function instead of the area so far function. Well, now that we've got this theorem, we can immediately get a bonus. We can prove, using it, that any two integral functions coincide. So, how are we going to prove this? Suppose we have two integral functions for f on AB, I alpha beta and j alpha beta. By theorem 1, we know that an integral function gives rise to a primitive, and we also know any two primitives differ by a constant, c, say. So, IAX minus JAX equals c for all x on AB. In particular, if we put x equal a, IAA minus JAA equals c. But let's look at IAA. By the boundedness axiom, little m times a minus a is less than or equal IAA is less than or equal capital M times a minus a. So IAA is trapped between 0 and 0, and so must also be 0. Similarly, JAA must be 0. Therefore, the constant c is also 0. So the constant by which the two integral functions differ is 0, and hence all integral functions coincide. So we've proved that an arbitrary integral function gives rise to a primitive, and as a corollary, we've proved that any two integral functions coincide for a continuous function f. But we haven't as yet proved the existence of an integral function, and that's what we're going to do now. We're going to prove that the lower integral gives rise to an integral function. Remember that the lower integral is defined using inner areas. So what we've got to do is we've got to check that the lower integral satisfies the two axioms for an integral function. To start with, the additivity axiom. Any rectilinear region on alpha gamma is the union of a rectilinear region on alpha beta and a rectilinear region on beta gamma. Conversely, any rectilinear region on alpha beta together with a rectilinear region on beta gamma defines a rectilinear region on alpha gamma. This implies that the least upper bounds add together, that is, the lower integrals add together. The lower integral on alpha gamma will be equal to the lower integral on alpha beta plus the lower integral on beta gamma. The boundedness axiom is easy. Since f is continuous, it is continuous on any subinterval alpha beta. And this means that it's bounded between little m and capital M, say. This means that the lower integral, the inner area under f, lies between two rectangles of heights little m and capital M and base beta minus alpha. And that shows that it obeys the boundedness axiom. So we've proved theorem 2, the lower integral is an integral function. And that's given us our first connection between integration and area, because the lower integral was defined using the inner area, and it gives rise to an integral function. Well, now we've actually proved that we've got a primitive, because you see, the lower integral is an integral function, and the lower integral always exists. So we've certainly got a primitive. A primitive exists, namely, the one given by the lower integral. But we've actually done a lot more than that, because you see, the argument that shows that the lower integral is an integral function, it works with very little change to show that the upper integral is also an integral function. So the lower and upper integrals are both integral functions, and we know that any two integral functions coincide. So the lower and upper integrals coincide. But that's exactly what we mean by the Riemann integral existing. In other words, we've proved that the Riemann integral exists. But the Riemann integral is now equal to the lower integral. The lower integral is an integral function. Any integral function gives rise to a primitive. So the Riemann integral gives rise to a primitive. In other words, we've got the fundamental theorem of the calculus which we set out to prove. Well, that's completed the argument, the main argument, but the logic was just a little complicated, so perhaps I should go through the whole thing and just summarize the steps again. We started out by axiomatizing integrals. We define an integral function to be something which just satisfies two axioms. We used those two axioms to prove that, provided the function was continuous, any integral function gave rise to a primitive. Any two primitives differ by a constant, so we deduced from that that any two integral functions coincided. Next, we proved that the lower integral was an integral function. And at that point, we'd proved that a primitive exists. But the argument that proved that the lower integral is an integral function proves that the upper integral is also an integral function. Any two integral functions coincide, therefore, the lower and upper integrals coincide. In other words, the Riemann integral exists. Finally, the Riemann integral is an integral function, so if we put it in theorem 1, if we substitute the Riemann integral for the arbitrary integral function, we get the fundamental theorem of the calculus, which says that the Riemann integral gives rise to a primitive. Well, in this program, we've successfully dealt with the problem of defining the area of a region under the graph of a continuous function. And from there, it's a short step to deal with the problem of defining the area of some more general regions in the plane.
Next week's programme for the course Introduction to Pure Mathematics will look at some of the effects of perspective changes on plane geometrical figures and show how these are related to the ideas of projective geometry